Warm greetings to everyone present here. In this video, we are going to see about the graph algorithms in design and analysis of algorithms. So, the graph algorithms are a fundamental part of computer science, focusing on analyzing and manipulating graphs, which are structures composed of nodes, that is nothing but vertices, and edges, connection between the nodes. So it is represented using adjacency list or adjacency matrices. So understanding these representation is essential for efficient graph algorithm implementation. So there are many kinds of graph algorithms like breadth first search, depth first search, Dijkstra's algorithm, Bellman-Ford algorithm, Floyd-Warshall algorithm, minimal spanning tree algorithms, topological sorting, then strongly connected components, graph traversal algorithms, network flow algorithms, etc. So depth first search, it explores as far as possible along each branch before it backtracks. Then it is often used in topological sorting, cycle detection, solving puzzles like maze and traversals. Breadth first search, it explores the graph by level. Starting from a chosen source node, it discovers all the reachable nodes from the source nodes till the final goal. It calculates the shortest path in an unweighted graph. Then in this video, we're going to see about the minimal spanning tree algorithms, where algorithms like Prim's and Kruskal's are used to find the minimal spanning tree of a graph, which is a subgraph that connects all the nodes. So it is a subgraph that connects all the nodes with the minimum total edge weight. So as I told it, it's a fundamental concept in graph theory in computer science. So where all the minimum spanning tree is of a connected undirected graph is a subgraph that includes all the vertices of the original graph while performing a tree, like that it should not form no cycle, that it should not form cycles and has the maximum possible sum of edge weights. The properties of a spanning tree is it spans all the vertices of the graph. It forms a tree with no cycle. Mainly, the point to be noted is it doesn't form cycles. It has minimum total edge weight. MSTs are not necessarily unique, but in graphs with unique edge weights, the MST is unique. So in MST, we'll first see about the Kruskal's minimum spanning tree algorithm. This follows the greedy algorithm and it is of undirected graph. First, it sorts all the edges of the graph by their weights. So here the weights is an important one. So the sorting is done by the edges of the graph by their weights. Then it starts the iterations of finding the spanning tree. At each iteration, the algorithm adds the next lowest weight edge one by one, such the edges picked until now does not form a cycle. It can be implemented efficiently using a disjoint set data structure. So it is a variety of practical applications such as network design, clustering and data analysis. When you ask how to find a minimal spanning tree using Kruskal's algorithm it sorts all the edges in non-decreasing order of their weight. First we have to pick the smallest edge, check if it forms a cycle with the spanning tree formed so far. If the cycle is not formed, include that edge. If cycle is formed, discard it. So it should be repeated until there are v-1 edges in the spanning tree. Now we'll see about the example of Kruskal's minimum spanning trees. Here there are 14 edges, like it is the connection between the vertices, and 9 vertices that are 1, 0, 1, 2, 3, 4, 5, 6, 7 and 8, which is of 9 vertices, and the connection between the vertices is termed as edges. So 14 edges are there. So the minimum spanning tree formed will be having of v minus 1, as I already told you. So here 9 vertices minus 1 is equal to 8 edges. After sorting, we'll see step by step. So first, from the mother graph, we'll be having the example. Now the first step is of selecting the smallest weight. So 7 to 6 has the smallest weight of 1. Then step 2, the next smallest weight is of 2, so that it is between 8 and 2. We have to select that. So the next smallest weight is of 2, which has a connection between 8 to 2, that is 2 to 8. Pick the edge 6 to 5. So no cycle is formed. We can include that. Next, step 4. Pick the edge of 0 to 1. The next smallest weight is of 4. So there is no cycle formed. You can include it. So the edge 0 and 1 is included in the minimum spanning tree. Next, step 5. So the next will be of 2 to 5, which has the same weight of 4. Next, step 6 is, so the step 6 includes, we'll be taking the next edges of 8 to 6. Since including the edge results in the cycle, it forms a cycle, so we can discard it. Next, we'll be taking the edge 2 to 3, that is, which has the weight of 7. Hence, there is no cycle is formed. We can include it. Step 7. Next, we are going to take the edge 7 to 8. Since this results in the cycle, we can discard it. Now, we'll be taking to 0 to 7 edge. As no cycle is formed, we'll be taking the 0 to 7 edges in MST. Then step 8 is pick 1 to 2. As if we take 1 to 2, this results in cycle. So we'll discard it. Then from 3, you can see the step 7. So from 3, we are going to take to 4, which has a weight of 9. So that is the Kruskal's minimum spanning tree. Next, we'll be going to Prim's minimum spanning tree algorithm. So as I told about the Kruskal, the same is of Prim's. It also forms the greedy algorithm. It starts by selecting it will be selecting a vertex and then adding it to the MST. It repeatedly checks for the minimum edge weight that connects one vertex of MST to another vertex that is not yet in the MST. So this process is continued until all the vertices are included in the minimum spanning tree. So to efficiently select the minimum weight edge for each iteration, this algorithm uses priority queue. So it will have a priority queue. So the data structure used is priority queue to store the vertices stored by the minimum edge weight correctly. So these are the results to be these are the steps to be followed for the Prim's minimum spanning tree algorithm. Basically, this algorithm starts with a single node, moves through several adjacent nodes. It has to visit all the nodes and explore the connected edges along the way. So there are 6 steps, like we have to take an arbitrary vertex starting from the vertex of the MST. The same has to be followed for 2 to 5 till there are vertices that are not included in MST. They are just connecting any tree vertex with the fringe vertices. We have to find the minimum among these edges. Finally, the chosen edge to the MST if it does not form any cycle. The last step is that return the MST and exit. So the example of a graph is, we have taken this one. The first step is, we'll be starting with 0. That acts as a starting vertex of the minimum spanning tree. Here 0 acts as a starting vertex of the minimum spanning tree. Next, step 2 is, like 0 can go to 1 and 7. It has a possibility of going to 1 and 7, but their weights are of 4 and 8. So basically we'll go for the minimum weight, here 4. So 0 is traversed to 1 through the weight 4. Next, 1 has a probability. It can go through 8, to 2 or 7 and 0. So 1 has a probability of going to 0, 2 and 7, or the 0 can even go to the next, that is the edges, which is of 7 with the weight 8. Then if you go with a 7, it has a possibility of going to 1, 8, 6 and 0. As 0 is already visited, we can have the choice of 11, 7 and 1. So this is the minimum weight. So we can choose the journey to 7 to 6 through the weight of 1. Next, coming to 6. 6 has the ways to 8, 5 and to 7. So as 7 is already visited, it has only possibility to go for 8 and 2. This the minimum weight is 2. So it obviously visits the 5 through the weight 2. Then 5 has the 5 has choice of going to 2, then 3, 4, and the 3 weights are 14, 10 and 14. So the minimum weight is of 4. So it visits this 5, visits 2 through the weight 4. Again from 2, so this 2 is already visited 8, so we can leave this, and it already visited by 5, we can leave this. The only thing is it visits 7 and 8. So this is the minimum weight. So the 2 visits 3 with a weight of 7. Hence it will have 2 to 3 and include the edge vertex 3 in the MST. So the vertex 3 is included in the MST. Next 3. Next 3 has the way 4 to go to 5, to 4 and to 2. So it is already visited, we can leave this part, and it is between these 9 and 4 weights, the vertex 4 remains to be included with the less weight of 9. So the final thing is, the final structure of MST is as follows, and the weight. So through 4, then 8, 1, 2, 4, again 2, 7 and 9. If you add all these edges, it will be of 37. The weights must be added, that is the edges must be added. So it will give the answer as 37. This is the final structure of MST. You can even have an alternative MST structure, that is this 0 can even go to 1, then to 8, to 2, then 4, then to 2, then 6, from here, then to here. So if you have selected the edges 1 and 2 in the third step, the minimum spanning tree would look like the alternative minimum spanning tree structure. So basically, if you see for Prim's algorithm and Kruskal's algorithm complexity, it is of O E log B time complexity, where then applications is of, it have numerous real world applications such as designing networks, telecommunications, computer networks, clustering algorithms and approximate solutions to the traveling salesman problem. It visits all the nodes and vertices so that it will be the same to the traveling salesman problem. Conclusion is, so the mastering graph algorithm is essential for efficient problem solving and algorithm designs. The knowledge gained from this representation will sure empower you to tackle the complex problems in various domains of computer science engineering. So basically graph algorithms, it visits all the vertices, edges. Thank you.